Next up is a theorem 2.1.2 about critical subgraphs. That theorem says that every graph G contains a critical subgraph H such that chi of H is equal to chi of G. Okay, so I have already gone and written this proof out, and so let's just take a look at it, and I'm just going to kind of uncover it a little by little here. Okay, so first off is we are going to prove this by induction on the number of edges that the graph has. Okay. All right. And so first off, starting with 0 edges, that's our base case, right? That would be this graph here, P0, also K1, whatever you want to call it. A graph that has one vertex, right, and no edges. And that is a critical graph itself, right? And so the subgraph would be the point itself, the whole graph itself. It is critical. Now you may say, hey, well, wait a second. How is that critical, right? Because in order to be critical, we have to have that if H is a proper subgraph of P0, then chi of H is less than chi of G, right? That's the definition of critical. And this thing doesn't have any proper subgraphs, so how can you say that it's critical? Well, remember that, just by logic, right, if I have a if-then statement, a conditional statement where the hypothesis is false, right, then that automatically makes the whole if-then statement true, right? And so no matter what subgraph you take out of here, the hypothesis is going to be false, right? And so that automatically makes the statement true in the end, right? And remember about the logic of the if-then statement. If you have if false, then true, that's true. If you have if false, then that's also true. So a statement like that, right, that's true, an if-then statement that is true because the hypothesis is always false is something, right, called a vacuously true statement. So that makes this graph critical. All right. Next up then is the induction hypothesis. The induction hypothesis, and that's what we are allowed to assume that's true, right? We assume the theorem is true for graphs that have less than or equal to k edges. Okay, so I'm using the stronger form of induction. All right, so we get to assume that every graph with less than or equal to k edges contains a critical subgraph H, such that chi of H is equal to chi of G. All right, so there's a critical subgraph that has exactly the same number as the chromatic number as the entire graph does. Okay. All right, and then what we need to show is if I have a graph with k plus 1 edges called G, let's call it G, right, we need to show that there exists a critical subgraph H of G, right, such that chi of H is equal to chi of G. So I have k plus 1 edges here. All right, so if G is critical, then we're done. We don't have to do anything further, right? Because the H, the critical subgraph, would just be G itself, okay? And obviously, G has the same chromatic number as itself. So really, we would have to not do anything there. All right, if G is not critical, then we know by the definition of critical, right, then we would know that there is a proper subgraph H1 of G such that the chromatic number of H1 equals the chromatic number of G. So remember the definition of critical, a graph is critical if every proper subgraph has chromatic number less than, right, the chromatic number of the entire graph. And so if that's not critical, right, that means by the negation of that statement there exists, right, a proper subgraph of H1 such that the chromatic number of the subgraph is greater than or equal to chi of G, but we've already proved, right, that the chromatic number of a subgraph has to be less than the chromatic number of the entire graph, okay, or less than or equal to. So that means that If a graph is not critical, you get, the existence of this proper subgraph with equal chromatic number. Okay. So now that subgraph may be critical, in which case we would be done, right? But it might not be critical either, right? So if it's not critical, then what are we going to do? Well, I claim that we can assume that H1 has less than or equal to K edges, okay, by the induction hypothesis. So why can we do that? Well, you might say at the very least you'd have to throw out something, right? If it's a proper subgraph, it's missing either an edge or it's missing a vertex. Okay. The one sort of flaw in there is it could be missing an isolated vertex, right? If you throw out an isolated vertex, there's no edges that get thrown out. Okay, so that would mean that H1 still might have K plus 1 edges in there, and that would kind of mess up our argument by induction, right? But the thing is that as far as colorings go, right, then the isolated vertex is not really going to mean anything because it doesn't have an edge to any other vertex, okay? So we can just throw out, right? We could have thrown out those isolated vertex. It's not going to change the chromatic number, right, at all. All right. So that means that something here has to, if we throw out those isolated vertices, right, then maybe the subgraph you get is critical, right? But in which case we're good, right? We have our proof. Or if it's not critical, right, then it has this proper subgraph, right? And so we could eventually kind of whittle our way down to something that has less than or equal to edges, unless all of the vertices are isolated, right? But at the end, if that's the case, we boil down to back down to P0 anyway, okay, which is critical. All right, so we can assume that H1 has less than or equal to K edges. So by the induction hypothesis, right, we get a critical subgraph H, right, such that chi of H is equal to chi of H1, all right? And so what you have, right, because then you would have H, that's a critical subgraph of G, right, because H would be a subgraph of H1. H1 in turn is a subgraph of G, so that would make that H a critical subgraph of G, and then the chromatic number of H, right, it's the same as the chromatic number of H1, which is the same as the chromatic number of G. So there is your critical subgraph, right, of G with the same chromatic number. All right, so by induction, this is true for a graph with an arbitrary, right, number of edges. Okay. All right. So that is it for this one, and then I am going to do the same thing and separate the subsequent proofs out on their own.